Okay.
For the last one.
Yeah.
So Nati, you have the floor.
Okay, thanks. Okay, so just recall where we were last time and where we're going. So we're talking about where, trying to understand where, how the choice of optimization geometry, like what type of steps you like to make, or what our local metric is in determining our preferred, our local updates, how it affects where optimization will lead us in an undetermined system where there are many global minima, and we want to understand which global minima. And what we talked about last time also is that we have our geometry in parameter space, and the geometry in parameter space is usually pretty boring. We're just doing gradient descent in parameter space, which corresponds to the standard Euclidean geometry. But really, what's important for us is this implied geometry in function space. So just to remind ourselves our setup, right? We think of our model as a map from parameter space to function space. I'll denote this also HW, or not, right? Where HW is just a function of x, which is the output of the model with parameter w and input x, right? But we think of it as just mapping w to this function from x to say the reals. And we also talked specifically quite a bit about linear models, where really then you can think of the mapping. We're abusing this capital F. You can think of the mapping just as a linear mapping. And what we saw is that we can actually describe how the geometry looks like in function space in terms of the Jacobian of our model F, right? So recall that we had that the dynamics in parameter space, and we wrote it at least for the linear model, were given as this outer products of Jacobians times just our times the gradient of the loss. And this is just gradient with respect to the function itself. And we identified this with just as the inverse metric tensor. And now what we're doing is just doing some gradient flow with respect to this inverse metric tensor. Right? So this is all just where we not ended, but what we talked about last time. Before, and then the two questions, or the type of questions we're going to answer today, or continuing answering today, is one is we asked how is this different than just doing explicit regularization on L2, because we saw that for linear models, if I just have a linear model in W, then we know that the implicit bias of gradient descent is just L2 regularization on W, corresponds to L2 regularization on W. And we saw that in some example we get something kind of similar. We already saw last time an example where I think we ended last time by saying an example in which it's actually substantially different. Another thing we're going to talk about today is how the loss function actually significantly affects the behavior. We talked about last time the squared loss is what you had in mind, but basically a loss, a regression type loss, where you really want to get you get zero loss if the output of the model is exactly equal to some finite label. And we'll talk today about how classification loss gives you different behavior, and also in that context revisit this like issues of scaling of initialization. And another thing we'll talk about is whether we can always kind of really think about things this way. Remember that in order to the steps we took to relate this optimization geometry to an implicit bias involved kind of two steps, which were two things that we couldn't generally do. One is we wanted to say that this metric tensor, which is inverse of the outer product of the Jacobians, really depends on where we are in parameter space. And in order to really describe this, such as some dynamics in function space, we have to be able to say that this only depends on where we are in function space. And we sometimes are able to do that, or with some tricks we're able to do that. We'll see another example today. And the other thing is that if this metric tensor was a Hessian map, then we knew that we could identify exactly the potential that it's derived from and identify that as an implicit bias. But in general, it would not be in a Hessian map, and we'll see today an example where it's not. Question?
Yeah, the gradient on the left-hand side is with respect to W, right?
The gradient, which gradient? Here?
Gradient of F.
Gradient, so this is the Hessian, yeah, this is a Jacobian of F. So F, right, is a map from W to, as I wrote it here, let's say, so really to function space, okay, although here it's just linear functions, okay, and this is the Jacobian of this map. So the derivative of, you can think of this as the derivative of beta with respect to W, okay. Is that answering the question? Okay. Okay, so actually the first thing I want to do before we start, let me erase this because we'll exactly do this, is if beta was linear, right, if the model was linear, we could exactly write it this way, and then it's easy to understand what F is, right, because capital F was just, so beta, in this case, right, this is just a linear map, so it's just a function RD, and W is also some parameterization in R. I'm going to use P. I know you guys use P for something else. It's very confusing for me, so now you're going to be confused. RP, okay, the number of parameters. What? Okay, now come on. I spend most of my life when M is the number of examples and N is a dimension. Fine, and then I go to, when M is number of examples and D is a dimension. And then I finally got used to statisticians which use P as the dimension and N is the number of examples. Fine, okay? But now I come here and P suddenly is the dimension? I mean, I don't know, that's, P is number of examples, that's just too much for me. Okay, I'm lecturing, you're gonna stick with P as the number of parameters. M is the number of examples. Okay, so in this case, where were we? In this case, the Jacobian is just a P by D matrix. Okay, I think it's useful to think about the more general setting where really forget the linear thing. Just H is a function, so H is just some function from X, say to the reals, right? And F is a mapping from W to this function. Okay, so what's a function? But the thing is that what's a function from X to the reals? It's also just this space of functions. Okay, is also just a linear space, right? It's a linear space. So it's just this is a mapping from RD to the linear space of functions. Okay, so to X to the R, right? And if you want to think of, sorry, what?
RD or RP?
This is RP, right? Sorry, I confused myself, right? Okay. Sorry, RP to, and this is also R to the X, right? Not X to the R. Okay. So it's also just a linear space of functions, and we can think of a Jacobian the same way. So if you're a computer scientist like me and you're afraid of like things that are continuous, then that's fine. You can just always think of, in your head, I don't know, probably most of you don't need this, I need this. Think for simplicity as X is just discrete but very, very, very large, right? And you can think of just enumerate all the elements, not just in your training set, but all possible X's. And this is just the vector of all possible, the output for any possible input, okay? I see the only one that's shaking his head is Boz because he's also afraid of continuous things like me, right? But now the question is, what is this inverse metric tensor, right? So this inverse metric, so what is the inverse metric tensor is now, so this thing, so now we're talking about H, right? And H here, so this is a vector, right? And this is the gradient with respect to the function. So it's a functional derivative. It's a function itself, right? So this is in R to the X, right? And this inverse metric tensor is a linear mapping from R to the X to R to the X. Okay, and we can. So how can we write it? I mean, think of it as just. You can think of it as a big. Again, I think of it as a big matrix, and we can write explicitly what. What its entries will be, right? So it's indexed by elements of x, and the x prime entry of it, right, would be. I'm running out of space here. Right? The x prime entry of it would be the product of rows of this of these Jacobian, other products of rows of Jacobian. So this is just what are the rows of Jacobian? Each row of the Jacobian is just the gradient of fw x prime with respect to w, right? So that's right. This is a derivative of the output of the functions with respect the output of functions h, which is just f of wx with respect to w. Oops, x. Okay. So what is this object? This is just the kernel metrics of the tangent kernel, right? But it's not. One important thing is it's not the tangent kernel at initialization. It's the tangent kernel at the current w. Right? Okay. So another way to understanding these dynamics is that we're not preconditioning. We're conditioning the dynamics all the time based on the kernel metrics at our current iteration. Okay, so in the kernel regime, what happens is this Jacobian doesn't change. And so this conditioning matrix actually doesn't depend on where we are in the space. It's fixed, at least in the space we can see. And the dynamics is just some preconditioned gradient descent dynamics. Okay, so it's just gradient descent dynamics under a different basis, and this is just, it boils down to a kernel method, right? We just do minimum L2 under some other basis. Okay? But more generally, this kernel matrix keeps changing all the time. Okay? It depends on actually where we are, and we get more complex dynamics. Okay? So this is another way to see kind of the relationship to kernel methods. Okay, but let's go back and let's go now to the logistic loss, and just to remind us how we motivated it. So we are looking specifically at the something. Let me actually let's talk about the. Okay, there you'll see. So just to finish our recap from last lecture, let me switch to a different color here. So this is all generic, right? But the specific model we looked as is an example, kind of the simplest model. We can already see this last lecture was this squared parameterization model, where really the model, or let's write it this way, the model really was just a linear model in X, but the parameterization with this second order parameterization, so model is given by w plus squared minus w minus squared, right? So this corresponded to this diagonal two-layer network. And towards the end of last lecture, we talked also about higher degrees, which corresponds to deeper models. And what we saw is that what we saw is that the implicit bias here depends on initialization. We initialize this always as with W naught just being uniform at scale alpha, so not a random initialization, right? But just all the parameters being W, which corresponds to in function space always initializing in origin. And we saw what happens as alpha changed. And in particular, what we saw is that if we look at, so we index B alpha as the dynamics when we initialize at scale alpha, and we optimize to infinity. We take time to infinity until we optimize it. And what we saw is that for d equals 2, this when when we take the initialization, so when we took the initialization scale to infinity, we got a kernel regime. We just got minimum L2 norm solution. We took alpha to 0. This is more interesting, and we got the minimum L1 norm solution. And the strange thing, though, so this was maybe not surprising because this is also the same thing we'd get with explicit regularization on the W's. The strange thing was that even when D was greater than 2, any depth greater or equal to 2, when we took the initialization scale to 0, we still got L1 regularization, even though with explicit regularization, okay, we'd get something very different. Right? So with explicit regularization, what we'd get here, let's turn to this color, okay? So what do I mean by explicit regularization? If we take the same model, and now our learning rule is that we want to minimize, can you see this color? I can't see it very well, no? It's not very good color. How about this one? Okay. We want to minimize, we explicitly minimize the L2 norm, right? Subject to having a zero error solution, so subject to Ls of f of w equals 0. Okay? Is the question there, or is it clear? Okay. Okay. So how can we understand this in beta space? So the thing is that over here, right, we call it this is just, this is just beta, right? And what we have here is that beta equals to this f of w, which is w plus to the d minus w minus to the d, okay? Now, if I'm optimizing over w, I'm never going to want both of these to be non-negative, right? The only reason I have here w plus and w minus is so I can get both positive and negative coefficients, okay? So always one of them is going to be 0, and the other one is going to have to take all of beta. And so what I get here is that for every, since this is happening element-wise, for every element of w, I mean, one of them is going to be 0, and the other one is going to be, you know, the one that's not going to be 0 is just going to have to be equal to beta to the 1 over d. Right? And so this L2 norm of w, right? So this is sum over all the coefficients of w squared may be, okay, so this is equivalent to minimizing this. I don't care about, you know, I'm not going to bother squaring it. Okay? And what is this equal to? So this is just sum of beta I to the power of t2 over d, okay? Subject to. Okay? So it's very easy to see what the explicit regularization we get. And I think this is where we ended last time. We saw that the implicit regularization is always L1, no matter the depth, and the explicit regularization is different. Okay. And now, what I promised you, so now we're ready to start the lecture. What I promised you is that in logistic loss, we'll also see a difference between them. So what we're going to do now is start analyzing implicit bias for logistic loss. Questions so far? Okay. So if you are a bit lost, now is a good time to restart because we are going to start basically from scratch. So let me erase actually so much in scratch. I'm going to erase all this. Okay. So let's go back to just the linear model. Okay, so that's where we started to understand the implicit bias with the squared loss and see what happens for the logistic loss. So we're looking at gradient descent on the loss of with respect to W, where this is just the logistic loss, so sum over our examples of the loss of W xi yi, where loss of y hat yi is just log of 1 plus e to the negative y hat. Right, so this is just the the standard classification logistic loss or cross entropy loss, and if you prefer to call it that way. Okay. Okay, and we're looking at gradient descent, so W, just write explicitly, WK plus 1 is WK minus some step size times, oops. Yes?
So what was the previous example for? What would we be observing?
What we observe in the end, that we see a difference between the explicit L2 regularization and implicit bias. So if you, if I just train this squared parameterization or this depth deparameterization model that I raised with gradient descent over parameterized model, I'm going to get to a 0 solution. The question is which 0 solution I'm going to get to. Okay, and in my implicit bias is only going to be determined by my optimization dynamics. Right? There's no explicit regularization. It's just where the dynamics prefer taking me. Okay, and you say, well, you're doing gradient descent on parameters. So this is a reasonable way to think. You're doing gradient descent on parameters. Gradient descent follows Euclidean geometry, okay, in parameter space. Maybe all that's happening is that you're just minimizing the L2 norm in parameter space. Okay, that's definitely the case for a linear model. Let's just guess that that's always the case. Okay, and now, and you're saying, okay, all I'm going to get. So you're not going to trust the dynamics. You're going to explicitly minimize L2 norm in parameter space. And I'm going to trust the dynamics. And the question is, do we really do the same thing? Okay, do we get to the same point? And what we see is that we don't. Right? You are going to find this minimum. So this is the minimum 2 over d quasi norm solution. Whereas I'm going to converge to the minimum L1 norm solution. Even so, for example, for depth 10, we're both looking at the depth 10 network. I'm doing gradient descent on the depth 10 network. You're finding the minimum minimum norm of the weight subject to fitting the data. Okay? Then the solution you'll find is going to implement a function which minimizes the 2 over d quasi norm of the predictors. And what I'm going to converge to minimizes the L1 norm of the predictors. And those can be very different, right? In particular, you're actually going to have much more sparsity than I am. Okay, is that clear? So the point of this exercise was to see that we should not take for granted the fact that that a gradient descent will just get the minimum L2 norm solution, and it's all just the L2 norm. Right? That the implicit bias of gradient descent can be actually very different. Once we depart from a linear model. The implicit bias of gradient descent can be different from just L2 in parameter space. Is that clear? Okay.
Assuming something on the labels here?
Where? Here?
Yeah.
Okay, so here the labels are binary. Sorry. I should say that. Sorry. Yeah. Thanks. So this is a classification problem, right? So this is a classification problem. The labels are binary, and we're just using this classification loss. We want WXI to match the sign of YI, right? That's what the logistic loss does. Okay, so now, right, so you have, right, so think of it this way. I have binary labels. I have points. Each one of these points is a point in RD, R2 in this case, because that's at most I can draw on the board. And each one has a label, right? The +1 or -1 is the label. And we train a linear predictor. W. And of course, the interesting case here is an overparameterized case, so the data is linearly separable, right? I can separate the data. And the question is, where is these dynamics going to take me? Right, so I said for gradient descent, I converge to the minimum norm solution. Okay, where am I going to converge to here? Where is WK going to converge to? Is the setting clear here, what I'm doing here? I'm optimizing the logistic loss for a linearly separable problem with gradient descent. Right, so where is gradient descent going to converge to? It won't converge, right? So it's a trick question. So the thing is that WK will not converge, it will diverge, right? Because to minimize this loss, right, the logistic loss is strictly positive, right? And to minimize the loss, I really have to take my predictions. So think of this as right, this is WX, right? So this corresponds to what happens with a positive label. To minimize the loss, I have to get it as close to possible to 0 I can. And the only way to get it close to 0 is to increase my prediction WX, and I can only do that if W goes to infinity. Okay? And if the data is separable, I can actually drive the loss to 0. Right? But I can drive the loss. The way I can drive the loss to 0 is I take some kind of. I can take any linear separator here, right? So this is defined by W, the normal to the separator. Okay, and now if I take W to infinity, right, then the predictions on all the positive points. If I take W to infinity, the predictions on all the positive points will be positive. The prediction on all the negative points will be negative. And as I scale W, they'll in fact be plus infinity or minus infinity. The loss will go to 0. Okay? But the thing is, I can do that along any linear separator. Right? So if I go in this direction, I'll go to 0. The loss will go to 0. If I go in this direction, the loss will go to 0. Right? There are many possible ways of driving the loss to 0. And really, the question I want to ask us is not, we don't care about W, right? What we care about the separator. And so what we want to ask is really, in what direction would W diverge? Because the direction of W, right, would determine what is our linear separator. Okay? So we're not exactly asking here what W converges, we're asking in what direction does W diverge, or in other words, we look at WK, normalization of WK, okay? And now WK is going to diverge, but this we hope is going to converge, and we're asking in where does this converge to? Okay. And so the claim is that this is going to, okay, maybe I can ask you for a guess, but my guess is many of you have already seen this. Okay, I hate it when people ask me this. Like, if you don't know the answer, then what's the answer? But if you haven't seen this before, what would you guess that? Which direction would you expect this will diverge? Or which linear separator? There are many linear separators here. The whole point is that the problem is underdetermined. Which linear separator do you expect to converge to?
The farthest away from all the points.
Yeah. Okay. So the furthest. When you say furthest, though, you have to be careful about how you measure furthest, right? So the furthest away from all the points in Euclidean geometry, because you're optimizing using gradient descent, which uses Euclidean geometry. Okay, or in other words, the max margin separator, right? So the hard, or you can think of it as the hard margin SVM solution, the minimizer of the L2 norm subject to YIWXI is greater than 1, right? Okay, and let me just correct this. So let's put it this way: you converge in direction that's proportional to this. The way, at least, I normalized here, this is not going to be unit norm. This is going to be unit norm. I'm not going to converge in the same direction as this, as the hard margin SVM predictor. Okay. Okay. So let's prove this, and the proof is going to be similar to what we had for the squared loss case, in that we are going to. I have here I'm just going to rewrite this in green. I'm going to write the same thing. I'm going to rewrite this in green. Oops. Okay, so we have this green problem, and the green problem is not the problem we're optimizing, right? The problem we're optimizing is the yellow problem, right? It's just the logistic loss. So this green problem has all kinds of elements that do not appear in the green problem. So it has this margin condition, right? There's no margin condition here. And more importantly, this L2 regularization popped up here in the green problem. It's definitely not part of the original optimization problem. And that's, again, that's the whole point of what we're doing here, that the original optimization problem did not involve any particular complexity, okay? Any particular complexity measure in W, any particular regularization, and this is coming only from the fact that we're using gradient descent, right? That we already kind of understand how, now, hopefully after the series of lectures, how optimizing gradient descent corresponds to Euclidean complexity control.
So Nati,
yes?
maybe I'm jet lagged, so just to make sure that
Yeah.
my interpretation of max margin is that you're getting the maximum over the maximum over W, say, of norm 1 over the minimum over I of eta I times
Yeah,
W
so,
xi.
right, so that's the same as this, right? So if you want to, okay, just for jet lagged people, if you want to, this would actually correspond better to the way I wrote it here. So, but it's harder to write the KKT conditions, so I'll do it next. So the way that Boaz wants me to write this is the arg min, the arg max. Okay, the arg max over gamma. Okay, such that yi. Okay, I'll write it. I think this is what you said. Arg max over gamma, such that yi wxi is greater than gamma. Right? That's exactly as taking the max over the min of these, subject to the norm of w is equal to 1. Right? Okay? Because this is really, if w is equal to 1, then wx1 xi is the projection of every point here in the direction of w. And so this quantity y times wxi really exactly measures this distance from the Euclidean distance from the margin, which is what Nati also mentioned. Okay, the thing is that these two are equivalent. Let me just put tildes here. Okay, and if I write, okay, I'm going to get the, if I write w is equal to w tilde divided by gamma, is that the right thing here? Yeah. So write w is equal to w tilde divided by gamma. Then over here, Buzz, this is for you. So okay, everybody else understands it. It's just okay. If you plug this in here, you get that yi times wxi is greater than 1. And since w tilde is normalized, the norm of w is just 1 over gamma. And so maximizing over gamma is the same as minimizing over the norm of w. Okay? Okay, good. But good excuse with the jet lag there. Okay, so I'm going to erase this because Buzz already understands it. Okay, so now, okay, so I have this implicit green problem, and I want to match the fact that by doing gradient descent on the yellow problem, then I'm actually minimizing this, and because this L2 norm of W comes up. And the way we're going to do this is, like we did before, we're going to show that the limit point of the dynamic satisfies the optimality conditions, the KKT conditions for this problem. And now, actually, I will have to use. Last time, people were annoyed that I called them KKT conditions because they're just simple optimality conditions. Now we have an inequality constraint, so we do have to actually be a bit more careful about the KKT conditions. So let's start by writing the KKT conditions for this green problem. Okay. So now, actually, so I'm not sure. So people here, so how actually, whether to spend 5 minutes on this or not. Are people familiar with KKT conditions for the SVM objective? Have people seen? So who has not seen, or maybe I'll say, who has seen the KKT conditions for SVM objective? I see. Okay, so not everybody. Okay, so let's just derive it because I think it's something. Maybe useful to see once how these optimality conditions look like for constraint optimization problems. Okay, so in order to derive the KKT conditions, we have to define their Lagrangian. So I've introduced dual variables nu. So we'll have a dual variable associated with each of these constraints. So nu here is in Rm. If I have m data points, and my Lagrangian is the norm. The objective, which is the norm of W squared, okay, plus nu, okay, I'm going to get the sign wrong, but that's fine, you'll correct me. I think it's 1 minus, okay, yi wxi, but actually, I'm going to, just to save some writing on the board and for you, let's ignore the labels, okay? So forget the labels. All the labels are +1. So without loss of generality, I can assume all the labels are +1. I mean, over here, just replace xi by xi times yi. So you can just suck in all the labels inside an xi, and it'll just save us some writing over there, right? So your problem really, all the data points are positive, and you want to find a half space that contains all of them, if you prefer to think of it this way, okay? Okay, so what are the KKT conditions? We have primal feasibility. So primal feasibility requires that wxi is greater. Oops, wait. This is sum over I. Okay, primal feasibility requires that, okay, so up to here everybody's fine. This is just, they looked at the Lagrangian of the constraint optimization problem, and since this is an inequality constraint, then we only need to think of nu of positive, non-negative nu. So we have primal feasibility, okay? We have the stationarity, so we have to set the gradient of the Lagrangian to 0. And, okay, let's make this a bit fancier. This is a Lagrangian, not the loss, right? Sorry. Okay, we have to set the gradient of Lagrangian to 0, so we have that W minus sum of nu I xi, right? If I take the gradient with respect to W, is equal to 0. In other words, W is just spanned by the data. Okay. And finally, we need a complementary slackness. So because this is a problem with the inequality constraints, right, then we need the only dual variables that are going to be relevant are dual variables for constraints that are tight. If a constraint is not tight, the constraint is irrelevant. So in other words, we have that nu I is strictly positive only when W xi is equal to 1. Okay, so this is, and in some sense, this is going to be the trickiest thing to satisfy. This is easily satisfied because we know, we always stay spanned by the data. Okay, and this is going to be satisfied just because we're going to normalize W appropriately. Okay, so now let's look at how the dynamics here look like. So what we're going to look at is, so I want to, okay, let's erase this. Okay. Okay, so first of all, we're going to approximate this logistic loss. We only care about what happens here. Right? We only care about what happens away from 0 because, eventually we're going to separate the data. And what we're asking is what happens, when we drive the loss to 0, when we really separate the data. And around here, this loss is just an exponential loss, e to the negative y plus, right? This is very, very small, and I can just take a first order approximation of the log. And really, all this analysis is not special to the logistic loss. It's valid for any loss that in the tail looks like an exponential, right? What happens here is completely irrelevant. Okay. 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 So now let's look at what direction we're going to do. And okay, so I'm going to warn you that what I'm going to do now is not exactly a proof, right? I mean, we have to actually be careful of a bunch of stuff because, in particular, I'm going to assume that lots of things converge. So I'm assuming we do actually converge in direction. And moreover, I'm going to assume that the gradient converges in direction. It is possible to actually be careful about these things and prove that everything converges. But if the gradient actually converges, okay, then we have to converge in the same direction that gradient converges. Because we're going to follow the direction of we're going to keep adding the gradient, and so that's the direction we're going to go. So let's look at what's how does the gradient look like. So the gradient with respect to W of the loss of WK, and we just need to take the gradient of this loss, so 1 over m, sum over the derivative of the loss, right? So this is okay, so I have a minus that cancels this minus, and the derivative of the loss is e to the negative wxi. Remember that we forgot about the labels times the data xi. Okay, so now, okay, sorry. So let's write it this way. Let's assume that WK actually converges in direction. So what does it mean that WK's convergence in direction? It means that I can write WK as the direction in which we go, W infinity, times some increasing function g of k, okay, plus some correction term. Actually, I called it R, but now I don't want to call it R. rho, okay, I'll call it rho, but this is different from the rho from before, rho of k, where really what we need is just that rho of k grows smaller than g of k, right? So then when g of k increases, and if g of k increases faster than rho of k, then the direction we're going to diverge is w infinity.
So rho of k is a vector valued...
No, rho of k is vector valued, right? So this is an r d, and this is just a scalar. Okay, right? So this is the scaling of w. So I mean,
RP.
what? Well, here p and d are the same because just a linear system, right? So p and d are the same. Okay, right? So g, right? Okay, but what we're going to assume is not just that rho of k grows smaller than g of k, but let's for simplicity just take rho of k to be bounded. Okay, so we have rho of k bounded, and this is actually what happens. We have rho of k, we have some kind of bounded fluctuations, plus an increase in the direction of w infinity, right? So that's the direction we go. Okay, and let's plug this into here. So we get the way this looks like is e to the negative g of k times w infinity xi minus this O of 1 times xi. Okay? Okay, so let's see what happens here. So this part, forget about, we don't really need it. And what's important is what direction is implied by here. Okay, so first of all, okay, and then we're going to define to match those. Okay, so I want to prove to you that this w infinity satisfies these k-T conditions. Okay, so w infinity, I have to normalize w infinity, right? W infinity is not normalized, depends on g on k. So of course I'm going to normalize it as what we're going to really look at is the normalized w infinity, which is w infinity. And I want to normalize it in a way that satisfies the conditions as I wrote them here. So I need wxi to be greater than 1. So, yeah.
So this gk and rho k implicitly depend on the norm of wk, right?
This
So
which?
that everything is normalized.
GK is equal
GK
to
is the norm of WK. GK is the norm of WK essentially. So GK is the norm of WK, and rho k is some like fluctuations in direction, right? So we have the way this is going to happen work, right? Is as I run gradient descent, I'm going to start optimizing, and I'm going to try to find the direction to separate. And then eventually I'm going to converge the direction that I'm going to separate in, which is w infinity. And then I'm going to keep going in that direction. So GK tells me how far I went in that direction is the norm. But when I go in that direction, I still have some other directions that are going to become insignificant as GK increases. So GK is essentially the norm of WK. Okay. So I want to. Okay. Sorry. Let's. Where was I? Okay. Sorry. I'm going to write this in a second. Okay, so now I want to take w infinity, and I want w infinity to satisfy these conditions. So the first thing I can tell you is that since I'm assuming here that I will actually converge to well, there's no global minimum, to a global infimum, I will converge to a zero solution. So that I know from, this is a convex problem, so it's really easy to say, but as we said, we never actually worry about the fact that we converge to a zero solution, we just ask which one. If we converge to a zero solution, I have to separate all the data points. And in order to separate all the data points, that means that w infinity times xi has to be non-negative. Okay, that's what it means to be a separating direction. Okay, and so in that case, if I look at the minimum over all I of w infinity xi, it's also positive. Okay, so let's call this. This is Boas's gamma, okay? And that means that I can normalize w infinity according to this gamma, according to this margin. Okay? Okay, so this normalized w infinity is going to be our candidate optimal solution for the KKT conditions that we're going to show satisfy the KKT conditions in the lift. Okay, so let's take this w hat infinity and let's see what we have here. So we already satisfied we already satisfied the first condition kind of by the way we constructed, this is greater or equal to, of course, by the way we constructed W hat infinity. Okay? The second condition is very easy to satisfy, right? Because we already talked about before, and gradient descent always stays spanned by the data. But let's look at what happens here. What are these nu going to be, right? So the nu are going to be some scaling of these things, right? So this is going to be proportional to nu I, right? Because I'm going to, at the limit I'm going to get to the same, the gradient is going to be the same direction as W infinity. And this linear, explicitly written here is a linear combination of the xi's. Okay? Okay, so now the main constraint that is a problem to satisfy is this complementary slackness. We have to ask which nu I are going to be non-zero. Okay? But think of what's happening here. What I really care about is this the normalization of nu I, right? So I have to normalize nu I. And so the only nu i's that are essentially going to be non-negative are the ones in which this, so this gk is going to go to infinity, okay? And all the ones for which this inner product is not maximal are going to go to 0. The only ones that are going to survive are the ones in which W infinity xi is, sorry, another way, W infinity xi are minimal, right? Because I'm taking, all of these are going to be non-negative. If I have, for some xi, W infinity xi is going to be 3, and for the other is going to be 7, the one that's going to be 7 as gk goes to infinity is just going to be driven to 0 relative to it. So the only ones I left with are the ones in which W infinity xi are minimal, meaning after the normalization equal to 1, okay? Which is exactly the complementary slackness condition that we have here. Okay? Okay, so what we established so far, okay, so is, where are my notes? Okay, so what we established so far is that for, we understood the implicit bias of gradient descent on a linear logistic regression problem. Okay? And we saw that similar to gradient descent on a least square problem, right, it also goes to something related to the minimum L2 norm. So now it's not exactly a minimum L2 norm solution, right? There's no solution. It's a minimum L2 norm margin solution with a margin. Okay. There are two things here, though, that are different. So one thing is that here actually over there we also need to take the step size. Okay, let me just jump forward. So you'll have to, you just have to trust me. The thing is that we can repeat this analysis and even for nonlinear models. So what we can show, let me switch to the slides now. It'll be a bit quicker. Okay. So this is just for for a linear model, and for a linear model we didn't see like a big difference between the squared loss and logistic loss. Both of them go to a norm solution. One thing we already saw is that this didn't depend on the initialization scale. So for the squared loss, remember that what we go is to the even for a linear model, we don't always go to the minimum norm solution. We go to the point that has the minimum Euclidean distance from initialization. Don't look at the board yet. Okay. This is blank, right? So we go, even for a squared loss, we go to minimum distance from initialization, and so the initialization is still important. And over here, for the logistic loss, we always the initialization doesn't matter at all. We always go to the minimum max margin solution. And this kind of makes sense because the point is for logistic loss, since we diverge anyway, we go infinitely far away from the origin, where does it matter where we started? Any finite initialization from far enough away looks like the origin. Okay? So keep this in mind because this affects much of the differences between the squared loss and logistic loss. The logistic loss forgets anything that happened in the beginning because it goes infinitely far away, whereas squared loss still, the whatever happens in the beginning has a finite effect on the end result. Okay, so now the main thing here is that what you can show is you can repeat this analysis and you can show that when you minimize logistic loss, then actually for any homogeneous model at least, okay, it's still the case that you always go to the minimum L2 norm solution, right? So now this is no longer a linear model. You can take any homogeneous model. For example, our diagonal neural networks of any depth, or if you want a ReLU network with any architecture, or these linear convolutional networks that we talked about before. Basically, any network with fixed depth and homogeneous activation, so ReLU or linear activations, and what you can show using basically the same proof is you'd always, you do gradient descent logistic loss, you'd always converge to first order stationary points of minimizing the L2 norm subject to getting margin 1. Okay? So we have to be a bit careful here, because what do I mean by first order stationary points? First order stationary points are exactly those points that satisfy the KKT conditions. For convex problems, that means you're optimal, right? We actually said we actually get to the minimum L2 norm solution, right? Here we have to be a bit more careful, because the objective is convex. That's not a problem. The objective is just an L2 norm, but F in general is not a convex function of W, right? Even for a depth 2 diagonal neural net, it's not a convex function of W. So these are not convex constraints. The Lagrangian is not convex. And satisfying the KKT conditions doesn't mean you're global optima. It just means you're stationary in some sense. Okay? But this gives us an indication that that's kind of what we're doing. In particular, it kind of suggests that what's happening is that if we look at it at function space, right, we can do, we're essentially also looking to kind of like stationary points of the induced regularizer in function space. So what is this induced regularizer? This is this representational cost, right? Minimizing, if really I was actually minimizing the L2 norm in parameter space, which point I'll get to? I'll get to the point in function space, the H, that has the cheapest representation in terms of W. Okay, the cheapest L2 norm in terms of W. So for every function H, I can ask what's the cheapest way to represent it. Okay, what's the minimum norm required in order to represent that that function H. Okay, and then instead of looking at minimizing W in parameter space, I can just look at minimizing this representational cost in function space. Okay, so these two optimization problems are equivalent in terms of their optima, in terms of their minima, in terms of a global minima. Is that clear? Right, that part? Okay. Okay. And now we can say, oh, we get to first order stationary points of this problem. Well, maybe we get to first order stationary points of this problem. Okay. So for example, for a depth D diagonal neural net, we already basically studied this representational cost, and we saw this representational cost is this 2 over D quasi norm. Okay, this 2 over D quasi norm is not right, this before this. Right, so this is not a convex function of beta. Okay? And in fact, I can't hope to actually minimize it. It's finding a margin 1 separator that minimizes this quasi-norm is an intractable problem. It's an NP hard problem. I can't expect that I actually get to the minima. What can I expect is, well, maybe I get to a local minima of it, right, or at least a first order stationary point. Okay? And this is kind of what this suggests. We have to be actually careful about it. It turns out it's not exactly the same. You can have stationary points in parameter space that do not actually correspond to stationary points of the implied regularizer. But in some cases, at least, you can actually prove that you do, in fact, get to stationary points of the representational cost in function space, including these deep diagonal networks. This is actually something we don't completely understand how to relate these two things, and whether it's true in general that you always get to stationary points for any model, any homogeneous model, to stationary points in function space.
That seems like a very, this representational cost seems like a very kind of complicated thing, because you're minimizing, you might have very, very different weight vectors that parameterize the same function.
That's true, right? So that's this argument is a very non-trivial argument, but this representational cost is a real thing, right? So this representational cost, in some sense, it's similar to what Chaim is doing, was he's integrating over W. Okay, so this is, it's a complicated thing, but in some cases you can actually do it. I'm not saying it's mathematically equivalent, right? But in both cases you're saying, I have some parameters, I don't really care about the parameters, I care about how the function looks like. Okay? And I want to understand what happens there. And in some cases, you can actually work it out. Okay?
And maybe
So-
you could say something like, you know, whatever is the representation, there is a sense in which moving locally in.
No, but the whole point is I want to get my point here is I understand the local dynamics, or there is some local dynamics, and I want to ask what implicit bias does it give me? Like, what am I actually? Can I say that I'm actually, minimizing some complexity measure in function space? Right. So at least in this case, I can say that I'm, locally minimizing this exact complexity measure in function space. I can identify the complexity measure in function space. Okay. Now there's okay. So now this result holds for any initialization, right? So I didn't care about the initialization here because we said I don't really care about the initialization because anyway I'm going to go to infinity. And now what you should ask yourself is what's going on here with the kernel regime? Like we're getting something which is different than the kernel regime, right? We're getting to these minimum L1 norm with depth 2 or minimum, 2 over depth quasi norm in higher depth. That's definitely different than what we get in the kernel regime, which instead in the kernel regime we'll always get to the minimum L2 norm solution. The tangent kernel for all these things is just the standard inner product kernel. And we said that when the initialization scale goes to infinity, we are always get to for an homogeneous model, when the initialization scale goes to infinity, we stay in the kernel regime. The Jacobian doesn't change. So it seems that those two things are contradictory. On one hand, I told you that, I think I have it even
but this
here.
was for the specific laws, for the cos entropy laws.
That's true.
But the kernel is mean square error.
Okay, no. So the kernel regime is not just for mean squared error. So you can write, okay, so the kernel regime is not just for mean squared error. The kernel regime is valid for any, So you can, what you need for the kernel regime, you don't need specifically mean squared error. All you need is that you need to be able to bound the derivatives of the loss. So as long as you have a loss with bounded second derivatives, you're fine. The thing is that, so okay, maybe I'll to answer Chaim, I can just give you okay. So recall that for the squared loss, the statement about the scaling and this is valid again, not just for the squared loss, it's any loss that has, basically you just need okay. Let's just stick with the squared loss for now, okay? What we said is that as the scaling goes to infinity, the entire trajectory converges to the kernel trajectory. Called the WK is the trajectory of the kernel problem. And so in particular, if the entire trajectory converges to the kernel trajectory, then also the implicit bias is the same as the implicit bias of the kernel, right? Because we just get the limit point of the trajectory is the same as the limit point of the kernel trajectory.
This is the square law.
This is for the squared loss.
Right,
Yes.
so this
Okay.
is different from this.
Right. So for logistic loss, you can also get a similar statement about how the scale going for infinity gets you in the kernel regime. But the problem is in the logistic loss, you can only get it for finite time. So if I fix the time of the trajectory, so I only I fix in advance how far I'm going to optimize, how long I'm going to optimize, and then take the scale to infinity, then I stay inside the kernel regime. So for any...
I'm sorry, in the quadratic laws, you want to get a solution with time.
That's true, right? So that's the difference in logistic and the quadratic, right? So for the quadratic, the entire trajectory is essentially finite time. And so if I take alpha to infinity, the entire trajectory stays inside the kernel regime. What happens in logistic loss is for any finite time, if I take the scale to infinity, within that finite time, I stay in the kernel regime. Okay? But, but what we saw here is that if I change this order of looking at the scale of initialization in how long I optimize, right? So what we saw is that for any initialization, okay, even if the initialization is very, very large, as long as I optimize far enough, I take t to infinity, eventually I'll escape this kernel regime. Okay? So another way, I'm just going to write the same thing, right? So we said that if I this holds, for any alpha, if I take the limit of t to infinity, and instead of looking at t, what I'm going to be showing you some plots. And what I'm going to be looking at is the optimization accuracy. Like, what is our suboptimality of our actually objective? We're going to call our objective here is just a logistic loss. So at any time t, I have some logistic loss epsilon t, the training loss, and this epsilon t is going to go to 0, right? Because that's we're driving the loss to 0. So let's parameterize things in terms of this accuracy epsilon t. So if for any initialization, if I drive the loss to 0, right, then what we see is that we get this for depth 2 network, the implicit bias is L1. Okay, so in particular also if you take alpha to infinity and then take the loss to 0. Whereas if we take the limits the other way around, if we first take the loss to 0, right, and then first look at the accuracy going to 0 and then take the accuracy to infinity, then we stay in the kernel regime. Okay? So it seems that like what's important for the transition now between, we still see a transition here between the kernel regime and the rich regime like we saw for the squared loss, but the transition now is not just based on a single parameter, which is the scale, but based on a combination of two parameters, the scale and the optimization accuracy. Okay? And you can actually, it's not too difficult, well, okay, so at least it's not too difficult to ask when will you enter the kernel regime. Like when, if you look at the kernel regime results, you can ask up to what time or up to what accuracy, optimization accuracy is for each initial, or I think easier actually think the other way around, for each optimization accuracy, at what scale will you enter the kernel regime? And the answer is that for initialization alpha, you're going to be in the kernel regime until epsilon is exponential in alpha squared, e to the negative alpha squared. Okay? And it turns out that this exactly, you can also have a complementary result that tells you that once you're past that point, you're in the rich regime. Okay? And on the boundary, the way this is going to behave, and now this is speculative, so this is or under a bunch of assumptions that don't hold in general, but what happens, and we'll see this also empirically, on the transition, you'll exactly behave according to this Q alpha function that we saw before, right? So we call it in the squared loss. We said that we could exactly characterize the transition between the rich regime and the kernel regime in terms of this Q regularizer of alpha, or alpha was a scale infinitization, where alpha was 0, we got L1, while alpha was infinity, we got L2. And here we get the exact same thing, but now as a function of alpha, the ratio of alpha to log 1 over epsilon, or square root log 1 over epsilon. Okay? So if I fix epsilon, right, and I take alpha to 0, I get into the L1. When I take fix epsilon, take alpha to infinity, I get L2. Similarly, if I fix epsilon and vary fix alpha and vary epsilon, I can see exactly a transition between them. Okay? So let's see how this looks like empirically. So what I'm showing you here, we actually optimized the logistic regression problem in 3 dimensions, right? So there's the predictor is a 3-dimensional vector, but we only care about its direction. Right, so I'm plotting just the direction of this vector. So the direction of the solution lies in a sphere. Right, so just the normal to our 2-dimensional separating hyperplane. And okay, you can't see it in this resolution very well. This is the sphere, and this is how the trajectory lies in the sphere. But what I'm doing here is I'm cutting a piece of the sphere, and I'm showing you some projection in it. Right, so this figure, this is not the error. This is not the test error. Right, this is just how the predictor behaves. Okay. And the way the predictor behaves is, so this is with some finite but not very large initialization scale, so initialization scale 2. Okay? So I start here, okay? And I know that eventually I'm going to converge to the minimum L1 norm solution. Right? So this is what this generic result tells us. For any initialization scale, if I optimize enough, I'm going to get to the minimum L1 norm solution. Okay? But on the way there, right, so when I start optimizing, well, first of all, it takes me some time to actually, do something. And on the way there, when my optimization scale is, when my optimization accuracy is finite, I'm going to actually traverse the entire Q alpha path. So what I'm showing you here, this is the path of minimum Q alpha margin solution. So each point here is the solution with margin 1 that minimizes the Q alpha for a corresponding alpha. Recall that alpha equals infinity is L2. And alpha equals 1, alpha equals 0 is L1. So this is some interpolation of L2 and L1. And what happens is I traverse this path and then get to L1. And as the initialization scale increases, as alpha here is going to increase, then I'm going to okay, I should qualify this. I don't know how to prove this, but this is suggestive of the result in what we see empirically, is alpha increases, I'm actually going to converge to this path. Right? So this purple curve is going to get closer and closer to this path. Okay? But the main thing I wanted to get from this figure is this number here. Okay? So it's true that we have an asymptotic result that tells us that asymptotically when we look at a homogeneous model, any homogeneous model, we're going to converge to the minimum L2 norm solution in parameter space. So again, going back to Avitek's question, why did I ask the question before? I want to try to understand whether doing explicit regularization and implicit regularization is the same. And we have this asymptotic result, and this is more generic, where was it? Very generic asymptotic result that tells us that for any homogeneous model, if I'm minimizing logistic cost of gradient descent, it's just the same as minimizing the L2 norm in parameter space. So I can be fine with this asymptotic result and be fine with it. But what we see here is that even though this is true asymptotically, the point in which it kicks in is just ridiculous. Right? So it kicks in, and this is a very benign problem with 3 dimensions, I think like something like 5 data points. Okay? There's a very, very small problem, and it kicks in only when the optimization accuracy, so this is not time, right? Time here is not very meaningful because we're talking about, I don't know, you can change the time by being fancier with how you optimize, take bigger steps and do all kinds of stuff like that. But the the training loss has to be 10 to the negative 2,000. Okay? None of you have ever optimized a network to a training loss of 10 to the negative 2,000. Right? I mean, it's just not like it's not a regime that's even relevant. Okay? And when we look at the more realistic regime, when the test loss is still close to 0, but not 10 to the negative 2,000, then we see a very different behavior. Okay? And this becomes even more significant when we go to higher depth. So same thing. But now we're looking at, it's going to appear in a second. This was with depth 2, and now let's look at depth 3. Okay? So at depth 3, asymptotically we know we're going to do the exact same thing. We're optimizing a 2-dimensional thing. We're going to go to the minimum L2/3 quasi-norm solution. Right? That's what the asymptotic theory tells us, and in fact we'll see the asymptotic theory is true. Okay, have to be careful with solution. A minimum, a local, first order stationary point. It's actually going to be a local minima in general. And these are actually these 2 points here in this space I cut from the sphere are the local minima of the L2/3 quasi-norm. Okay, but when I start optimizing here, what's going to happen if I optimize? I think the initial scale is 3 here. Then again, what I'm actually going to first go, in this case, actually very close to minimum L2 norm solution. I'm going to traverse the Q alpha path. So my effective regularization is actually going to be the same as in squared loss. And only then when my training loss is here, it's 10 to the negative 4,300. I mean, these numbers are just absurd, right? Only then will I actually get to this asymptotic regime and actually get to where my asymptotic theory tells me. Okay, so at least for me, this was, when we did this, I actually, I didn't actually believe these plots, okay, because this was really a bit of a, I thought, okay, we have an asymptotic understanding, that's fine, right? I mean, we drive the loss to 0, and so we have a result when we drive the loss to 0, understand what's going on. And now I looked at these plots and I don't understand anything that's going on. Because, the asymptotic regime here is just irrelevant. And again, I should say that we don't actually, it seems that what's happening, as I keep saying, is that we traverse this Q alpha path and then go here, and so the relevant action is probably here, but I don't actually know how to prove it. And this happens when moderate initialization. When the initialization is small, then the behavior is different. So if we initialize instead with an initialization scale of 0.1, so a relatively small, but again, not minuscule initialization scale, then we see we don't actually traverse this Q alpha path, right? Only initialization scale increases we'll get here. And instead we go directly, more or less, to a local minima of the 2/3 quasi-norm. And then, okay, I didn't plot to you the suboptimality, but this is actually with reasonable suboptimality, okay? So, and I have to say, I don't actually understand exactly what's going on here, right? So, I mean, we understand the situation when alpha is large. Right? And when alpha is large, I don't know how to prove you'd get here, but it seems that that's what you'd get there. And again, you get something which is very different with an explicit regularization. And so again, the initialization scale does seem to be relevant also for logistic regression problems, but we don't know actually how to really say what happens here when the initialization scale is small. And just to put things into context, when initialization being small or large, recall that we talked about when we have, oh my God, we talked about when we have width, then the width also affects the effective initialization scale. That a wider network has effectively larger initialization scale, even if the output of the network has small scale, right? So we might be, the width can also control whether we're here or we're here. The other thing I just want to point out before we move on is that this characterization, saying that we get to a first order stationary point of this non-convex function, is not fully satisfying. It doesn't actually tell us where we get, right? Because initialization, there are multiple first order stationary points, multiple local minima, and depending on the initialization scale, we get to different ones. Okay? In general, if I look at more and more complex problems, then even if I can write some kind of representational cost, it's going to have tons of local minima, and perhaps the more important kind of effect of the optimization is which one of these local minima of the representational cost we're going to get to, right? And this isn't, all this analysis, it's just based on matching KKT conditions, is not going to answer that at all. Okay, but at least maybe it's a first step towards that direction. Okay, I do want to talk about matrices, so just before that, I just want to advertise this model. I mean, until now we talked just about this very simple square parameterization, or maybe dth order model. You can ask many questions just in this model. So in particular, you can ask so this is for me the appeal of this model is this is the simplest model in which you can see any of these effects. So if you want to start studying these effects, start with this model, and you can ask questions about what is the effect of different optimization parameters like step size. So Kavya, who is here somewhere, has some work on that. On what happens if you change the shape of the initialization. So we have some partial understanding of that, but actually there's some interesting open questions here that are relevant for continual learning. Like if you train and then train again, initialization, you initialize in something not just as different scale, but different shape. And there's still questions here we don't understand. And maybe the most important thing is how does stochasticity affect the implicit bias? If I optimize with gradient descent and Boaz optimizes with stochastic gradient descent, okay, Boaz is definitely going to do much less work than me. I mean, so what we definitely understand about stochastic gradient descent is that it's much more efficient computationally. Okay, both because each step is going to cost them much less, and it turns out that you can also optimize with less steps. But fine, we have patience. I mean, Chaim just left, but I learned from Chaim. We're not worried about time. We have patience. So we're going to optimize to infinity. Are we actually going to get to different places? So in convex models, we're not. So the only advantage that Boaz has over me by using stochastic gradient descent is going to get there much faster, but we're going to both get to the same place. But for non-convex models, I'm not sure. And in fact, there's some work by Nicolas Flammarion and students that actually, Scott is not here. I don't know this person actually, so he's not here, right? Okay. That suggests that there's at least some small differences, but I'm not entirely sure if this is due to step size or stochasticity actually, because it's still a bit more complicated, and this is definitely something we want to try to understand. Okay, but in the remaining 15 minutes or so, what I want to do is go back to our general methodology, which is identifying the geometry, and then saying, remember what we did is we identified the geometry, and then found a Hessian map that a potential function such a geometry is given by a Hessian of that. And let's see the limits of what we can do. So the model we're going to look at is we're going to go from vector models to matrix models. So it's very similar to before. We're still going to look at essentially a linear model in beta, except now we're going to think of beta as a matrix, but really this is just how we think about it, right? Because x beta is going to be just some linear operator over beta. Okay? And so this is just a standard least square objective in beta where I just organize beta as a matrix instead of as a vector. Okay? So far, there's nothing new here. The main difference is we're going to factorize beta, and instead of looking at factorizing beta element-wise, is u squared or u times v element-wise, we're going to factorize beta as a matrix product of u v transpose as a matrix. Okay? So these type of matrix problems capture many things. We talked about matrix completion a bit in the first lectures. And you can also, but this is, so matrix completion, right? You want to recover the entries of beta, that corresponds to x, where the xi's, the linear measurements, are just indicators over specific entries. But you can also think more generally if you have multitask learning, so each column of beta corresponds to a different task, right? So you hit, then the x's are matrices with only a single row or column, depending on how I wrote it here, active, or you can think of it as a two-layer linear network also. You can think of, this implements a linear transformation from x to y, which is given by some product of u and v. Okay, but for us, all this is not important. What we're going to ask is if I do gradient descent on the factorization, then what is the implicit bias in function space, in this case in metric space. Okay? And so let's follow a methodology we did before. So we do gradient descent. We're going to replace the gradient descent with gradient flow, take the step size to 0. And so the dynamics are governed by these differential equations. The w dt is equal to the gradient of the loss with respect to u, and the v dt with respect gradient with respect to v. And what I want to know is to know what the dynamics on beta. Okay? And we already know that the dynamics on beta, the beta dt, are given by the gradient of the loss with respect to beta. So this is gradient with respect to beta times this outer product of the Jacobians. Okay? So in this case, maybe it's easier to look at it this way rather than, I mean, I could, take this in and plug it into beta, but I can also work with this directly. The Jacobian here is very simple. Our model is just beta is u v transpose, so the gradient of beta with respect to u is v, and the gradient of beta with respect to v is u, right? And you have to just be careful with how you arrange things in matrices. And when you multiply on the left or on the right, and what you get is the dynamics are so this outer product of the Jacobians corresponds to this linear transformation. So remember, this is going to be a linear transformation of the gradient, and this linear transformation is multiplying on the left by u transpose and plus on the right by v transpose. Okay? So again, you can also work this out directly. What I mostly want to get here is it clear how what's written here is just a linear transformation of the gradient, and this linear transformation is this outer product of Jacobians. That's a metric tensor. And now, recall that we had two problems. The first thing, as we said, is can we identify this inverse metric tensor, okay, which in this case is this linear transformation, just in terms of beta. So here it's written in terms of u and v, but we want to understand how the dynamics look in beta space. So we don't want u and v there, we just want beta. And we actually can't do it here. Because even if I tell you what beta is, I don't know, I know what uv transpose is. Uv transpose is beta, but I don't know what uu transpose is, and I don't know what vv transpose is, right? There are many ways of factorizing it, and in this case, unlike the case we saw before, we can't actually work backwards. Okay? So what we have to do here in order to understand the dynamics is add information to beta. Instead of just think of the dynamics in metric space, in beta itself, we're going to have to look at a richer space. And the right augmentation here turns out to be the same thing that actually we did when we talked about depth, and maybe I didn't go into much detail there, so this is another chance, and to go into this lifted symmetrized problem. So so what we looked before is just uv transpose, right? So that's beta. And what we're going to look now is we're going to look at our parameter matrix W. This is exactly our parameters. I'm just looking at U and V together. And I'm going to look at the entire matrix WW transpose. Okay? So we're going to call this beta tilde, right? That's going to be our new kind of enriched function or matrix. It's going to include beta on the off-diagonal blocks, right? So now I have right in here, but I can just look at, I get the same problem where x, I can write x tilde as just, lift the observations also, and my observations are only on this off-diagonal blocks. Okay? But now when I track what's going on, the geometry in function space, in metric space, I'm going to track it in terms of this entire matrix. And now I also have UU transpose and VV transpose. Okay? So I'm going to look at this. So think of it in terms of W as again a matrix factorization problem. The only difference is now it's a symmetric matrix factorization problem. Okay, so this corresponds to a minimization problem for matrices that have a symmetric factorization, or in other words, positive semi-definite matrices. Okay, so what we showed you is just whenever you have a non-symmetric matrix factorization, it's always a special case of a symmetric matrix factorization, a PSD problem in higher dimension. But in some sense, this is kind of the real problem you should be looking at, because looking at a non-symmetric one hides information about the geometry, but that tells you, which direction to search. If you look at the dynamics in beta tilde space for the symmetric lifted problem, then now I can write it directly as same as before, as WW transpose times the gradient plus the gradient times WW transpose, but WW transpose is just beta, right? So now I can write it directly in function space. So in other words, this metric tensor that inverse metric tensor we had before, what controls where I'm searching is just a function of where I am in parameter space. What I have here now is this means that what I'm doing gradient flow at least on the matrix factorization is completely equivalent to searching in the space of matrices with this specific with the metric tensor that's given, the local geometry that's given by this metric tensor of multiplying on the right and the left by beta tilde. Okay, so now let's just focus on this. We're gonna not drag along the tildes. Everything here is now in the lifted space. I just removed the tildes so I don't have clutter. Okay, so we're back to this dynamics, and let's try to understand how this dynamics looks like. Okay. So what we want to see is whether we can identify it as a Hessian map. Okay? But actually, recall that when we identify things in the Hessian map, that also corresponded to saying that the dynamics stay inside the low-dimensional manifold. Right? That's what we did before. So can we identify also here that this dynamic stays inside the low-dimensional manifold? Okay? So let's just write down, to do that, let's expand this out and write down this the gradient of the loss explicitly in terms of the residuals. Okay, so the gradient of the loss, this is just the gradient of the loss with respect to beta, right? So it's just the residuals times the x's. It's written, we have to write it in a maybe stranger way, because I can't just write times, because I'm thinking of x's and matrices, so I'm writing it as applying a linear operator, right? But this is again just taking the sum of the xi's times the corresponding residuals. And now again we get a differential equation in beta that's controlled by these residuals. And recall the trick we said before. I said we don't care about the residuals. The solution of this differential equation always stays inside the manifold. Is this the case here now? Any quantum physicists? There are people here who have background, right, in quantum physics, much more than I do. So is this stay? What you see what's going on here? Okay. So the thing is that as long as these xi's commute, okay, then we can actually solve this differential equation. And the solution to this differential equation is basically like the scalar case. I just multiply with e to the sum of the observations times the integral of the residuals, just like I had in the scalar case. Okay? And in this case, I can actually identify a manifold. So this is going to be my manifold here. It is exactly going to be like the scalar case. And this because where I am just depends on the integral of the residuals so far. So it can be this way. What happens every time I see a non-zero residual for any infinitesimal step, I multiply on the right and on the left with the corresponding observation metrics. Okay? The residuals tell me how much I'm multiplying with each observation matrix, right? If I have a high residual, I'm going to hit it more with that observation matrix. If the observations commute, it doesn't really matter which order I multiply with these, I order them, so it doesn't matter in which order I see the residuals. What's important is just for each observation, how much residuals total did I see, right? This is this integral of the residuals up to time t. Okay? And this is just, again, a vector in Rm. And so my matrix beta stays inside this m-dimensional manifold, right? So that's just equal to all matrices, of this form. It doesn't really matter what this form is. What's important is just it's an m-dimensional manifold in this d by d dimensional space. Right? Again, we're underdetermined problem. M is much, much smaller than d by d. Okay? And in this case, we can do everything we did before. We're down to a d-dimensional manifold. We can cross it with the observations, get the implicit bias, or we can also get the implicit bias directly by looking at finding it's a Hessian map. So okay, I'm not going to go over the details, but you can do this as an exercise later. If you restrict to these, the things you're always going to stay here, everything is going to be jointly diagonalizable. If you just stick to matrices that are jointly diagonalizable, over those matrices, this is our our metric tensor. Right? A metric tensor is just a linear map, and a linear map that's given by mapping A to multiplying on the left and on the right by beta, depending on remember then what's the metric tensor for every point beta? It maps every point beta to a linear map. Right, so every point beta here maps to this map, and we can ask whether it's the inverse of this metric tensor is a Hessian map. It is. We can find out Hessian map of what. So it turns out the potential function is this entropic potential, and we kind of understand everything that's going on here. And so so this is kind of the easy situation, and representative of all the situations we saw before. So we see two things happening here. One is that the Hessian map. The metric tensor is a Hessian map, and the metric tensor being a Hessian map actually directly implies that we're staying in the low dimensional manifold. Okay, because the metric, we already understood that if the metric tensor is a Hessian map, what we're doing is essentially mirror descent, and mirror descent we know we stayed inside the manifold. And they should say that in that case the result is kind of very robust. It doesn't actually depend on the actual residuals. We'll stay inside the manifold no matter what residuals you have. The residuals are the derivative of the loss. That means that it doesn't actually matter which loss we have. If I use a squared loss, right, and somebody else uses an absolute value loss or any other type of loss, okay, then it's going to affect the residuals, but it's not going to affect the manifold. Okay, and so as long as we get to a zero solution, we're going to get to the same zero solution because there's a unique point in that manifold that's actually a zero solution. Okay. So this result is very robust. What I just want to emphasize they're not robust to is the step size. So gradient descent, you always get the minimum L2 norm solution even with finite step size. Here you don't. Why is that? Because for gradient descent, the manifold was linear. And so even if you take finite steps, you stay on your manifold. What's going to be here, we're limiting ourselves to some manifold, but it's a curved manifold. So the residuals determine kind of the steering on this manifold. And so as long as doesn't matter what the residuals are, we stay on this manifold. But if we take a finite step size, we do kind of a ski jump off the manifold. Right? And then this is no longer valid. Okay, but the more complicated case is what happens if you're non-commutative, and if the measurements don't commute, then now it's actually important in which order I multiply on the right and the left. And what I get now is I can still write the solution beta t as in terms of the residuals, but now I get this time-ordered exponential. I know nothing about time-ordered exponentials. I discovered this for the first time when you got this thing, and then I went to a colleague and said, what does this thing look like? Oh, so that's a time-ordered exponential. Okay, hopefully some of you know maybe about them more than I do. But the point is now I can still describe where I'm going to get to at time t in terms of residuals, but I cannot completely ignore the residuals now. So now what happens is that what's important is not just the sum of the residuals, but also the order of the residuals. And in fact, I'm not staying in the low dimensional manifold here. I can get, even if I have only two observations, before I was restricted to two-dimensional manifold, here even with two observations, if I combine them the right way, like if in the right order, I can get to any point in my metric space. Okay, so this seems strange, at least it seems strange to me. Maybe to you guys it doesn't seem strange. And the way I was explained to it is it's like parallel parking. So when you drive, you're in a three-dimensional space, right? Your car is a three-dimensional state, the location, which is two-dimensional, and the orientation. And your control is only two-dimensional. You can go forward or backward, and you can rotate right and left. So you only have control over two operations in a three-dimensional space. But somehow, you can actually move in directions which you don't have control over, right? So by combining the moving backward and forward with the rotating right and left, if you do it, I move forward, forward, rotate, backward, rotate, backward, rotate, do this, then integral of the moving forward and backward, you stayed in place, right? The integral of the residual is 0. The integral of the rotating right and left is 0, but somehow we move to the right, right? And that's kind of what's happening here. Okay, so my characterization in terms of that ignores the structure of residuals breaks down, and I have no idea how to analyze this. Okay, so this is kind of, and unfortunately, this is the case in general, right? So the cases we know how to analyze are these super special cases where things commute, and then we don't care about the residual. We should just look at their integral. But what I really would like to understand is we still can characterize here exactly what optimization geometry is in function space. It's a well-defined question. I optimize with this geometry in function space. Where do I get to? Which global minima do I get to? Intuitively, it would still just depend on geometry. I should not move. I'm not going to go very far away in this geometry. To parallel park, you have to take a very long path. There's absolutely no reason you'd really take this parallel parking, like infinite path, in order to like get to a zero solution. You'll probably get a simpler path, but I have no idea how to characterize it. Okay, let me finish here. So the approach I was trying to convey in these series of lectures was trying to understand the implicit bias of neural networks with a complexity theory approach, which kind of decomposes the problem to saying that optimization biases to a particular, there are many zero solutions, right? That's, okay, this part is very, I think, non-controversial. We're optimizing an underdetermined, overparameterized model. There are many zero solutions. We're going to get to a zero solution, but which zero solution, why does it generalize? And the approach I've been sort of trying to present is to decompose the problem into two parts. One is to be able to identify kind of which solution do I get to by identify some relevant complexity measure and saying that I'm at least approximately minimizing this complexity measure. And once I understand that complexity measure, I can then study, is this complexity measure a good inductive bias? Does that actually give me generalization? Okay? And then just to complement the question, in order to understand whether it's a good inductive bias, they both have to understand what is the generalization properties of it. So bound the capacity of sublevel sets of the complexity measure, roughly speaking, or maybe use some other arguments to say that minimizing this complexity measure is good. And then say it also captures reality well, that reality has good complexity under this measure. Okay? The question is this complexity measure approach at all at all the answer. It's not clear that I can actually you can explain things using a complexity measure. So that means that there's some evidence that in some settings we have an algorithm that generalizes well, even though and we cannot explain how well it generalizing by relating it to any complexity measure. Okay? And I think that from my perspective, I think we're still not sure how much we can push this complexity measure approach. My feeling is that even though there's some specific, there are some settings and we can say it doesn't work perfectly, I feel that for many problems we're encountering, we still see that you can get a long way with it, and I still think it can capture a lot of what we're seeing, and this is kind of what we've been seeing here. Okay, so I'm going to finish here, and we'll maybe be in time for lunch. Thank you.